In the previous video, we got as far as having a 5 volt to 3.3 volt interface that allowed the pico to read signals on the ZX81 expansion port, but I hadn't got as far as allowing the pico to send data back to the ZX81. This turned out to be quite a frustrating task for this week, but also, in some respects, easier than I thought. The difficult part was learning how to do this with the PIO commands, or quite limited PIO commands, on the pico. And the easy part was that the potential divider of the pair of resistors will work quite well. So the clip that you can see playing at the moment is the ZX81 is sending out its I/O requests on port 4, and the pico is responding by sending back a predetermined sequence of characters, bytes I suppose, that represent characters on the ZX81. It was meant to be a photograph of Einstein, but something got lost in the translation. I showed in last week's video had a mistake on it. It connected ROM chip select to earth, which is going to damage your ROM and your RAM if you do that. So I corrected that at the time and put a note out. But yeah, don't do that. That's a bad idea. The ROM chip select doesn't need to be connected at all. It was meant to be earth that was connected to earth. The KiCad schematic was correct. I made some changes to the resistor dividers. I extended the 1K and 2K resistor dividers to cover also the control signals, as well as it being on the data buses. I'm not sure this was actually needed, but in confusion at one stage, I think I'd made an error in the programming, and I thought it might be the resistors causing a difficulty. Also had a message in the last video with someone suggesting that I should really use level shifters, and that does make a lot of sense. But since the resistor divider network seems to be working at the moment, I'm going to carry on with it for a while. Just check how reliable it is, and move to level shifters later if needed. It might not look much, but hopefully when I plug this in, 255, so I need a short assembler program just to show the results of the input-output read on the screen. So here's my I/O read. This one's just reading the keyboard as a test, and then down here I'm reading from port 4. The keyboard is port 2, so reading from port 4, and then just displaying the numerical value on the screen. Holy crap! So hopefully you saw that. So 255 turned into a 254. Oh, it's all a bit flaky, but essentially that's the bit 0 of the data bus. So in order to program the programmable I/O effectively, it's good to have an understanding in your head as to how it's structured and how its structure relates to the operations that you can perform on it. So you've got an output shift register and an input shift register. These are connected to the main CPUs, either if you're running code on the CPU itself or if you're using an interrupt routine, by two FIFOs. So the output shift register can get information from the main cores through its FIFO. I think they call it the transmit FIFO. And the input shift register can send information through its first in, first out queue, and that's called the receive. It's a bit confusing that it's called the receive, because I guess that the computer receives information from the input shift register, and the main cores transmit information to the output shift register. I guess that's what that is. And of course the output shift register then can take that information and put it out to the world, so maybe that's a little bit more what it's like. Then I suppose the next important thing you've got is you've got your pins and your pin directions. Your pins you can both read to them and write to them, but the pin directs, as far as I know, you can only write to them. Then you've got a couple of scratch registers, X and Y. So that's your physical layer, if you like. That's your computer layer, and then here's your PIO state machine. Let's call this the state machine, really, layer. You've got a couple of commands. You've got set, and then you've got in and out. Both these commands need to be enabled before you can use them. That's just like the main takeaway from this week for me. This one, I think it's called sm_config_set_set. And this one's the same smconfig set_out. So yeah, if you don't enable them, they're not going to do anything for you. I think that's just in relation to setting the pins with them, that they need to be enabled. You can play with them transferring information amongst the registers, but for the pins they need to be enabled. Set has the restriction that it can only be used with numbers up to 31, so 5 pins, 5 bits. In and out have the restriction that this is only shift only. You can't, so that's like, set is like your random access memory, and in and out is like your shift memory. With both set and in out, you can set a base pin, which is where it's going to start its operation. So if it set its base pin there, then it would operate on the 5, 1, 2, 3, 1, 2, 3, 4, 5, is that right? And out's the same. For shifting, you can set a base pin, so you might want to set the base pin there, for example, and then it would use those ones. This base pin for set will apply to all of these in and out commands apply to the X and the Y, the input shift register and the output shift register, and the pins, not the pin directions. In doesn't apply to the pin directions, whereas out does. So that comes back to this one-way nature of pin directions. So out does. Now you can set the output shift register and the input shift register to shift either left or right. Left, right. And same with the output shift register. Left, right. So if it's shifting to the left, it will take however many bits you ask it to shift out, and it will take those and it will put them into a new number, which will be the bits that you asked it. Say if you asked it to take 5 out, and the rest it would set to 0. If you ask it to shift to the right, it will take the, so having checked that, your base is considered to be the least significant bit of the register. If you're shifting to the left, it will take the most significant bits. So if you can think about the base as where the data is going to disappear into. It's like the siphon that's going to suck the data out. So if you're shifting into the left, quite clearly the most significant bits are going to be sucked into the base, and if you're shifting to the right, your least significant bits are going to be shifted into the base. It's a difficult concept to get, but it's really handy when you do. So think of it like a siphon. Same for the input shift register, ISR. And then whatever bits are sucked out, whether they're sucked out from the most significant bit or from the least significant bits, it doesn't matter. They're always going to be put as the least significant bits of the thing that of the 32-bit number that you're constructing. And then this 32-bit number will be put in your destination, whatever your destination was, whether it's pins pinned as X or Y, or the input shift register. Each of these two registers, the input shift register and the output shift register, have got a counter. So we'll call that your out count, and that one your in count. And these counts relate to the push and pull instructions. So there are two ways that push and pulls can happen. There's the manual way and the automatic way. If at any time you want to take the contents of one of these two registers and either push the input shift register out onto the receive FIFO, or pull the contents of the transmit FIFO into the output shift register, you just say push or pull. But you can also set these, these have got a flag as well, let's call it the auto flag. That was going to be your output auto, and that was going to be your input auto. And as well as there being a flag, there's also a number associated with that flag. And that number is the number that count needs to reach before an automatic push or pull occurs. So if we set the number at 1, it would mean every 1 bit that we shift into the output shift register, every 1 bit that we shift into the input shift register, as soon as the count gets to 1, it pushes that number onto the FIFO and clears the input shift register. But if we had the count, if we had the number set to 32 and it was at auto, it would have to wait until all 32 bits had been pushed into the input shift register, and then it would automatically push out and then clear the register. These FIFOs are quite short. I think, I can't remember, is it 3 or 6 words that they can contain? Not very many. And if they get full, then I think out and in might stall, so that's something to be aware of. You really want to be telling whoever's at the other end to do something with the information you're sending through an interrupt. Whew, that's quite a lot of information. But it's not awfully well written down in one place, so it does take a while to get the hang of everything. Finally got it working. It's reading, waiting for a I/O request on I/O port 4, I/O port 4, and then it's just doing a loop with the Y register and a NOP 10 in there as to slow it down, starting from 31 and then printing out the number it reaches. So it's getting down to 17 or 18. So that's 17 or 18 times 10 at 130 megahertz, and that should time for the amount of time that the I/O request is low for an I/O request on port 4. So we'll see if that's the case. But I find this quite promising, and the ZX81 is generating that I/O request, but it must be getting 0 back, I guess, because I've got the I/O port set as input. So the next thing to do, I suppose, is for the duration of this I/O request, is to set the ports to output, set the pins to output, pin dir, and provide it with some kind of value. There are several ways to do this, but the one I've chosen, the data pins are the low 8 pins here, from 0 to 7. And then the next 5 pins are the I/O request, read, address 4, which is the address pin I'm going to use for this port, write, and memory request. So I want to look for these 3 being low to indicate there's an I/O request read on port 4. So I set X register to those bits, then left shift those bits into the input shift register, and then I left shift the first 8 bits of Y into the input shift register. So the reason I do this is just so that whatever the data is, it's just going to be comparing the status registers. So there's probably other ways to do this that are simpler. This is the way that I've learned to do it. So now I've got what was read in the output shift register and what I want it to look like in the input shift register. So just move both of those into Y and X and then do a jump that compares X and Y. If I haven't met this condition of the control pins, then it jumps back and reads in the pins again and repeats until it finds itself at a IO request read with A4 low. And I've got the assembler program to send off one of these requests every second or so. So when that condition is true, I set the pins to output, set them to 0. I don't think I need to set them to 0 every time. Basically, I'd already set them to 0 somewhere else. I think I set them to 0 here in the C. I'll actually set it to 1. So I probably do need to set it to 0. Yeah, set it to 0. Then just for records, I push the input shift register and call an interrupt request, so at least it shows something on the terminal whilst I'm running it. Then I wait for pin 8 to go high again, which will signal the end of the interrupt IO request. Set the pin down as to input because we don't want it to be outputting values whilst the ROM and the RAM are reading and writing. And then jump back to the start again. It just goes around this cycle. So no data is passed to and from this routine. It's just it's just basically changing the pin directions. And this took me a long time to do, mainly because I was unaware of this very important command, which smconfig set pins. So I've got it basically you need this to enable you to be able to set pins. Without this, you can set and reset all you like. Nothing's going to show on the output port. That took quite a while. Another thing that was quite confusing was I haven't used it here, but you can set a jump pin. And you also set the base of the in pins. So I was playing around with that quite a lot. Because the big problem is that you can only, when you're doing all these set routines, you can only set them with numbers from 0 to 31, so just 5 bits. Well, I've got 8 plus 5 bits of information that I need to play around with. So it gets quite tricky to manage to get the right values in the register. There are ways to do it. Here I've used the input shift register and the output shift register, and I've shifted bits in and out. I think that's perhaps the easiest way to do it, but it takes a while just to get used to. You also have to be careful that you turn the auto push off, because that's what some problems I was having, because I'm inputting null just to clear the input shift register. And of course with the I had the auto push on to start with, and that was pushing it away. And when you push repeatedly without clearing it somewhere else, as I do here, push and then clear it in the interrupt, that causes the input shift register FIFO queue to get full, and I think then the state machine halts. So lots of learning there. So whilst I was struggling with the errors in my code, I wondered if I was having difficulties with the electronics. So I put the scope on the signal from the clock as it reaches the pico, the ZX81's clock as it reaches the pico, and got this ugly sawtooth wave. I thought this was due perhaps to the stray capacitance in the circuit, which had been shown on the microchip diagram I showed last week, which I had thought was a capacitance that you had to put in yourself, but that was an error, and is actually just showing the stray capacitance in the circuit. And I've certainly will have a lot of stray capacitance in my circuit. But actually this sawtooth is just because I didn't realize I needed to put the scope on the times 10 impedance level. So once I got that sorted, it looked like this, which gives me a great deal of confidence that I can carry on just with the simple resistor divider network for now. So here's the output now when I'm responding to the blue I/O request, and the yellow is the data naught pin as I've turned it from input to output and then set it high. So it responds quite quickly. But here I've, even though at the end of the I/O request I set the data pin to input again, it remains high on the circuit because the circuit will be high impedance. And here's the same thing just over a larger time span. You can see the charge, I suppose, on the data line decaying exponentially. Also, you can see the previous I/O request, which the code ignored because that was a keyboard reader. So it was an I/O request for read, but just on a different port FE. And in this trace, once again, see the I/O request in blue, and this time I've changed the data pin to a value of 0, one instruction before changing it to an input, from output to input. And you see it's just about had time to lose half of its charge. So it's looking a bit neater. And then finally, I put another 2 cycles of delay in there. So 3 times 130 millionths of a second. So it's rather fun to be able to have that much control over a signal through software. A bit of information every time the ZX81 does an I/O request on port 4. It's just toggling the value of the bit that it sends back, and that's showing on the scope. And then here we can see the ZX81 responding to that changing bit. So that's pretty good, though last time I plugged it in there was a little bit of noise. You can see every now and again there's a bit of noise. I think that one in the top left is something I did deliberately. But yeah, it's drawing an image to the screen. And that's all coming over the port there. And I think if there is a little bit of noise, yes, it's to do with the resistor divider network, but also it's to do with all those wires. So I guess that's the next thing to do, is maybe do some longer tests on where's the noise coming from. Do I need to get rid of those resistor dividers and put in place this chip here that I've got, this level shifter. But we'll see, that looks pretty steady at the moment. It's continuously passing the same number through to get that. I think it's character number 8. So yeah, pretty steady. Happy with that.